Hello everybody, today I'll talk about failure analysis of electrostatic discharge and electrical overstress. Failure of this component is called GAS, EAS, MMIC. This semi-amplifier ESD damage is electrostatic discharge damage. And it is short and fast and has a high amplitude pulses. ESD has been ranked the second most important cause to affect the yield and the reliability of integrated circuit (ICs). So it's ranked the second most important cause. Number one is the electro-migration. ESD event can often occur by inadvertent handling, so by accidents. The number two is electro-overstress damage. Electrical overstress damage is generally associated with over voltage or over current stress for long-term duration. and it's considered as one of the most frequently occurring failure mode in semiconductor devices. This one here is the GAAS MMIC, is the gallium arsenide monolithic microwave IC, this component. And it's used in telecommunication products, TV receiver for satellite broadcasting and in-radar navigation systems. Electrostatic discharge can damage the gate localization in GAS substrates, causing cracking of the device gate metal or localized melting. This is the ESD damage, and the electrical overstress damage can cause melting of small amounts of device layers. This has consequences of two types of failure, electrical failure: short circuits and open circuits. Let's talk about some experimental approach in this case study. First of all, electrical overstress has been applied with specific excessive voltage. This voltage has been increased step by step by 5 volts until the failure occurred. So most devices in this case study showed failures of voltage differences of 20 volt. So when the voltage reaches 20 volt, there will be damage in this device. There are 3 common electrostatic discharge test models. So we have 3 test models for electrostatic discharge. First of all, HPM or a human body model, when a charged human body touches an IC. So when the human touches the electrical component, there will be electrostatic discharge. This is the machine model, when a charged machine touches an IC. Charged device model, a charged IC touches the grounded surface. So in this case study, HPM or human body model was performed in this experiment. This flow chart shows the steps or the procedure in the experiment. First of all, we have a visual inspection, then non-constructive test, so we don't damage the samples. Then we hypothesize potential failure modes, mechanics, then the destructive physical analysis, then comes the test of destructive, then failure site signature, then find the failure mechanism. The whole procedure here called FMEA evaluation. After that, we establish assessment and test plan and identify causes. So we know the causes. After this, we know the causes of the failure. So we can identify the root cause. So we can improve the system or improve the component according to this root cause or something. If we don't know this, so we go here. We make ESD EOS simulation with number of devices. Then we make a correlation with actual field failures. That's it. After that, we make a prediction of the load. Let's talk about another issue. It's about a burn-in process. What's a burn-in process? It's a process usually done in the first life, in the first period of the component life, at the film life, before it goes to the field or the service. The firms don't want defective products to go to the field, so they make this process to assure that all products that goes to the service is defective free. For example, this is the burn-in process. We have a round computer component put in this chamber. This chamber has a very high temperature, and when it is tested, this door is closed for a specific period of time. After that, we accelerated the conditions for this. Serial cause by burn-in process are mainly due to ESD and EOS damages. The device from HPM ESD showed short failures. So all of the devices that are tested in the HPM or human body model, ESD showed the short failures. But in the EOS damage, 3 failures are open and 1 failure are short circuits. An important difference between the 2 types of failures are the size of the damage site. So with ESD, a microscopy called a scanned electrical microscope must be used to view the damage area. With EOS, the area of damage can be observed in a low power optical microscopy. So the damage area for the electrical overstress is larger than the area of electrostatic discharge. That's it.